Therefore, from proposition 3 and axiom 1, we can conclude that the probability is between 0 and 1. The minimum value is 0 for impossible events. The maximum value is 1 for a certain event or sample space, and for other events the probability lies between 0 and 1. And finally, proposition 4. For any events A and B, please note that here these events are not disjoints, same as the results from axiom 3, that we proved that for the union of finite collection of disjoint events, but here A and B are not disjoint. For any events A and B, the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. But how we are going to prove this proposition? From this Venn diagram, you can see that this the first one diagram. The first diagram shows the union of A and B. The second one is A, and the third one is B minus A, or A prime intersection B. We talked about all of these Venn diagrams in previous videos. So we can write the union of A and B as the union of two disjoint events, A and B minus A, or A prime intersection B. You can see that this part and this part doesn't have any elements in common. So this A and B minus A are disjoint. So from the results from axiom 3 for finite collection of disjoint events, we can write that the probability of union of A and B is the probability of A plus probability of B minus A, or the probability of A prime intersection B. Now we should obtain this part, the probability of A prime intersection B. For obtaining this part, again, we consider B as the union of two disjoint events. We can consider B as the union of two disjoint events. Again, you can see that this part and this part doesn't have any elements in common. This part shows A intersection B, and this part again shows B minus A, or A prime intersection B. So again, because they are disjoint, we can write that the probability of union of two disjoint events is the probability of the first one plus the probability of the second one. So the probability of B is the probability of the intersection of A and B plus the probability of B minus A, or the probability of A prime intersection B. From this equation 2, we can write the probability of A prime intersection B is the probability of B minus the probability of A intersection B. By substituting this result in equation A, we can prove the proposition 4, as you can see in this page. So instead of the probability of A prime intersection B, we can substitute the probability of B minus the probability of A intersection B, and at the end we have the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. Again, please note that these events are not disjoint, because if they are disjoint, we don't need this part, because all of us know that for disjoint events, A intersection B is empty, and from the proposition 1 we know that the probability of null events or empty events is 0. So for disjoint events we don't need this part, and we can and the result is the same as axiom 3. But if A and B are not disjoint, you should obtain the probability of A union B from this equation, not axiom 3. And also we can extend these results for from 2 events to 3 events. For 3 events, the probability of Z union X union Y is the probability of Z plus the probability of X plus probability of Y minus probability of intersection Z and X minus probability of intersection Z and Y and minus the probability of intersection X and Y plus the probability of intersection of Z, X and Y. To prove this equation you can see page 62. Please memorize these equations. The probability of A union B, the probability of A is 1 minus the probability of A prime. The probability of A minus B is the probability of A minus the probability of intersection of A and B. And similarly, for the probability of B minus A or A prime intersection B, we can write that this is the probability of B minus the probability of A intersection B. Now we are going to solve an exercises. It's a very important exercises. Please practice this several times. A marketing survey indicated that 60% of the population own a car, 30% own a house, and 20% own both a house and a car. Calculate the probability that a person chosen at random does not own a car. Okay, at first, what we have that 60% have car, 30% have house, and 20% have both of them. So we can write it as this. What are the assumptions? If we consider A as owning a car, then the probability of A is 60% or 0.6. If we consider B as the owning a house, so the probability of B is 30% or 0.3, and the probability of owning both of them, it means both of them we can write it as owning a car and owning a house. Intersection is equivalent to and. So we have the probability of A intersection B as 20% or 0.2. By using these three values, we are going to solve our problem, our exercise. First, the probability that a person chosen at random does not own a car. Okay. For 1, when owning a car is A, does not own a car is A prime. So in number 1, we should calculate the probability of A prime. A prime is not owning a car. So from for position 2, we can write this is 1 minus 0.6. It means 0.4 or 40% of the population don't have any car. And also you can understand it better by using a Venn diagram. For example, we have this is the population that have car, is the population that have house, and this one is both. So the population that don't have, or the individuals that don't have a car is this area. It's A prime. So again, the probability of A prime is 1 minus probability of A. A is 60%, so 40% of population doesn't have any car. own a house. Okay, again similar this one. It's the car. This one is B house. This one is both. These people here in B, here they have house. It means outside this area they don't have house. It's B prime. So the probability of B prime is 1 minus probability of B. It's 1 minus 0.3 is 0.7. It means 70% of population doesn't have any house, doesn't own any house. Just owns a car, not a house. It doesn't mean that you always see this part. Maybe you just see, okay, calculate the probability that a person chosen at random just owns a car. Okay, for this part, again, for 3, I think 3. We have this one as A or car, this one as B or house, and this one both. It means it told us just owns a car. Okay, it means this area, not both. Just owns a car. What is this area? It's A minus B. All the elements in A that are not in B. It's A minus B, and the probability of A minus B is the probability of A, as I told you before, minus the probability of A intersection B. So the probability of A, the car, is 0.6. The probability of A intersection B is 0.2. So the result is 0.4. It means the 40% of population just owns a car. Just owns a house. Again, similar to the number 3, we can say that, okay, it's the car for A, it's the house or B, and it's both. Just owns a house. It means this part. What is this part? It's B minus A. It's all the elements in B that are not in A. So it means just house. And the probability of B minus A is the probability of B minus the probability of A intersection B. The probability of B is 0.3 minus the probability of the intersection is 0.2. So 10% of population just owns a house. Just owns one of them, a car or a house, but not both. Just owns one of them. Okay. Again, we have car, house, and both. Okay. Just one. It means just car or just house. Just house. Okay. We showed that just car is here. Just house is here. Or is union. Just car and just house are disjoint. Because you can see that the red lines and the green lines doesn't have any elements in common, so we should just obtain the sum of the probabilities for just car and just house. For just car, we obtain in from number 3, I think we obtained 0.4, and for just house from number 4 we obtained 0.1. So the probability for just one of them is 0.5. Okay, if I want to write more tidy, we can write this like this. The probability of just one is the probability of A minus B plus the probability of B minus I. A minus B was 0.4, B minus Y was 0, and the answer is 0.5. Okay, number 6, owns a car or a house. Or at least one of them. At least one of them, it means owns a car or a house or both of them. Look at here, a car or a house, not both, but here we need the both of them. At least one of them, it means a car or a house or both of them. But also from this, from or, you can understand that you should use the union of the car and house, or A and B. the union of A and B. So for number 6, car or house, it means A union B. So the probability of the union of A and B is the probability of plus, you know that A and B are not disjoint because the probability of the intersection of A and B is not 0, is 0.2. So we use this equation. It's 0.6 plus 0.3 minus 0.2, and the result is 0.7. And if you want to show it as a Venn diagram, it's this area. A or B. It's the union of A and B. Number 7, owns none of them. Okay, for this part, again by using Venn diagram, they have car, this part have house, A, B, and here both. And we say owns none of them. So the area is here. No car, no house. So how we can obtain this area? All of us knows that the probability of S is 1. So we should write that 1 minus probability the union of A and B, because this blank area is the union of A and B, and the probability of the rectangle is 1. So the probability of the blue area is 1 minus the probability of the union of A and B. So is 1 minus 0.7 is 0.3. And the last one, owns at most one of them. At most one of them, it means one or less. It means one or not, or anything or nothing. 1 or 0. At most one of them. Okay. How we can solve it? We know about the none. It's the none of them. So this area, the blue area, is none of them. And before in part 5, we shows that the area of one of them. So at most one of them, it means one of them or none of them. So we can write like this at most one is one or none. So again, or is union. Okay. It's car or A. It's house or B. It's both. Okay. One of them is the red area. It means just car or just house. One. And none of them, it's the green area. So we need the union of red and green, but we can obtain it with the complements of this area. It means at most one is one minus the only area that is blank here with no color is both. It means 1 minus the probability of A intersection B is 1 minus 0.2 is 0.8. So at most 1 is 1 or none, or 1 minus both of them. Complement of this area is this blank area. The complement of 1 or none is this blank area. It means both of them. So instead of obtaining in a straight way, we use the proposition. What was the number of the proposition? We use the proposition 2 to obtain the answer. So for at most 1, it means 1 or none of them. It means 1 minus both of them. So is 1 minus 0.2 is 0.8. Or also you can, because this green area and this red area are disjoint, you can add the results of the 1 and the results of the none. You can obtain the sum of them. It means the one of them plus none of them, because they are disjoint. For the for one of them, the result was 0.5. Okay, for one of them, and for none of them, the result is 0.3. Again, you can see that here we can write also 0.5 plus 0.3 is 0.8. Both of them are same. Please practice these parts from part 1 to part 8 to understand them completely, and also please memorize these equations as well. Thank you.